Courses in the cement industry. Present to you. Bypass system, in the cement industry. Course 1. A bypass creates a valve for circulating elements, in the rotary kiln and removes elements, such as chlorine, sulfur, and alkalis until the coating, or clogging situation in the preheater, rotary kiln becomes controllable with the help of cleaning. A bypass is used for the removal of alkalis, in case low alkali cement is being produced. Figure shows, mimics bypass system, in the cement industry. Figure shows, CFD simulation streamlines, of the preheater cyclone of a cement plant. Figure shows, CFD simulation temperature map, of the preheater cyclone of a cement plant. Table of contents. Introduction. Circulation phenomenon. 1. Internal and external circulation phenomena. 2. The limits of chlorine and sulfate, input in the rotary kiln feed, on loss on ignition-free basis. 3. Maximum allowable input of volatiles, in the rotary kiln with pre-calciner, loss on ignition-free. 4. Circulation mechanism. 5. Evaporation rates of different elements. Solution. 6. Molecular ratio of sulfur, and alkalis. 7. Optimum range of molecular of sulfur, and alkalis in the presence of chlorine 13. 8. Coating and ring formation, in rotary kiln and preheater. 9. Where does the buildup occur, in the rotary kiln and preheater system? 9.1. Rotary kiln. 9.2. Cyclone preheater. 10. Behavior of volatile in preheater, with precalciner. 11. The relation between kiln system, and the volatile matters. 12. What is the reason that makes suspension, preheater rotary kilns with precalciners, more sensitive to the volatiles problem, than the suspension preheater rotary kilns? 13. How to decrease the effect of volatile matters, on the rotary kiln system. 14. Measures to overcome the circulation problem. Note. Bypass installation in, dry process. Bypass system. Introduction. Bypass system. It is well known that cement is made mainly from limestone and clay. Both contain the essential oxides, silicon dioxide, calcium oxide, aluminum oxide, and iron oxide needed, to form the clinker. 4 major components in the rotary kiln. These 4 oxides exist in limestone and clay, in different percentages. Limestone and clay have also other minerals, that contain some elements that are not required in the process, of forming clinker main components. Some of these minerals exist in different percentage. If these percentages exceeded certain limits, then it creates trouble for the burning process, especially, in the preheater lower stages before and after the precalciner, in the rotary kiln inlet area, and sometimes in the rotary kiln tube itself. These elements and components are called process adverse materials. These harmful materials are sulfur, chlorine, and alkali elements, sodium and potassium. Their behavior in the rotary kiln and preheater atmosphere leads to a buildup of layers of these components, and trapping huge quantity of rotary kiln dust. This buildup forces the rotary kiln operator to shut down the rotary kiln system to clear this buildup, that in most cases makes the operation next to impossible. The rotary kiln operation suffers, because the buildup in the riser pipes, and cyclones increases pressure drop in the system, so maintaining draft in the rotary kiln, becomes harder and more difficult. This obliges the rotary kill operator to work with less excess air in the rotary kill, which makes things worse since the circulation of sulfur highly increases at low oxygen level, and the problem becomes worse in the rotary kill, and the buildup of accretion becomes very quick, and its nature will be stronger and harder. The buildup will be harder to clean. This leads directly to a decrease in rotary kill production, and eventual shutdown of the system. The second result of working with higher levels of sulfur circulation is the formation of a very dusty clinker. This leads to deterioration of the heat profile of the rotary kill and preheater system because high amount of heat will be lost with the dust transported with the rotary kill exhaust gas. This will shift the heat upward away from burning zone, affecting the coating condition in the rotary kill burning zone. The rotary kill then will have a long zone of unstable coating at the upper transition zone, before the burning zone leading directly to brick in this area, since with every cycle part of the brick that is approximately 10 mm will be lost. The only real and final remedy for this phenomena preventing it from troubling the burning process is to install a bypass system. The sole and major job of this installation. Bypass installation is to control these elements to the degree that permits for smooth operation. Therefore, a universal fact should be noted, that the bypass system does not eliminate the circulation problem of volatile matters but just controlling it to the degree that makes the rotary kill operation smooth and economical. This section is devoted to study in detail the problem of the volatile matters in the raw materials, and the bypass system and how to make it work smoothly. Circulation phenomenon. This term is used to represent the phenomena caused by the presence of the volatiles in the system. As alkali chlorides, sulfates, and other related components in the dry rotary kill system, with preheater and precalciner. Why this phenomenon is called the circulation phenomenon. The circulating elements are sulfur and chlorine, and the other two elements are sodium and potassium. Fractions of these four elements first evaporate in the rotary kill burning zone, depending on the degree of volatility of the component, then carried away by the rotary kill gas in the direction of the rotary kill inlet, and condensate and precipitate on the kill feed particles in the preheater lower stages, and in the rotary kill inlet, then return back to the rotary kill burning zone again, and volatile again. So they start to circulate in the system between the rotary kill and preheater stages, and will continue endlessly to evaporate in the burning zone of the rotary kill and then precipitate in the preheater. We follow circulation phenomenon. They return to the rotary kill burning zone with the fresh material containing a fresh supply of these elements in addition to what is precipitated on them in the preheater. However, we have to note here that part of these elements leaves the system with the clinker, the preheater chimney, the preheater electrostatic precipitator dust, the bypass chimney, and bypass electrostatic precipitator dust. These cycles continue as long as the rotary kill is in operation, and bypasses the process is called circulation phenomenon. These cycles increase the concentration of the alkali sulfates and chlorides in the system to a very high level, as the operation of the rotary kill continues. Such concentration increases to 50 times its original concentration when the rotary kill is just started. We follow circulation phenomenon. 1. Internal and external circulation phenomena. The inner circle of volatile matters, or internal circulation phenomenon, is between preheater tower lower stages and the rotary kill burning zone. As for the volatile matters that condensate on the material particles of the rotary kill feed and have the chance to leave the rotary kill system, with the rotary kill gas leaving the uppermost cyclones, they precipitate in the preheater electrostatic filter, and eventually returning back to the rotary kill, with the fresh feed, but they just enrich the feed with these volatile matters to some degree. Their cycle from preheater to electrostatic precipitator, to rotary kill feed and back again to the rotary kill system, is called the external circle of volatile matters or external circulation phenomenon. At a certain concentration, the system atmosphere becomes saturated to the degree that permits for the precipitation of the volatile matters in the melted phase condition that will lead to the formation of build-ups and rings in the lower part of the preheater system, and the rotary kill inlet and in calcining zone in the rotary kill. If the concentration of the volatile matters becomes dangerously high, either because of high input of volatile matters to the system, or due to high volatility of these matters, then the installation of a bypass system is a must. We follow circulation phenomenon. 2. The limits of chlorine and sulfate input in the rotary kill feed on loss on ignition free basis. There are two limits. The normal limit, which is applied when the rotary kill feed has moderate to normal silica modulus and normal value of free lime, will be accepted in the clinker. While the high limit is applied when the rotary kill feed is easy to bum, have low silica modulus accepting higher free lime in the clinker, and the alkali and sulfur ratio in the rotary kill feed is ideal. The high dot limits should not also be applied when the condition in the burning zone require very strong flame, as in high silica ratio in rotary kill feed, or the rotary kill feed has a relatively high volatiles content, and we need to produce low alkali clinker cement from this feed with concentration of volatile matters in the rotary kill feed higher than the ideal concentration needed for low alkali clinker. We follow circulation phenomenon. 3. Maximum allowable input of volatiles in rotary kill with precalciner, loss on ignition free. In this table it is explained normal and high limit for sulfate and chlorine. If these limits are surpassed, and the total input of volatiles are higher, the precalciner rotary kill should be provided with a bypass system, by which a part of the rotary kill gas can bypass the preheater altogether. This process decreases the concentration of volatile matters, leaving the rotary kill to the preheater and precalciner. The bypass percentage of the rotary kill gas can be calculated in the following way. Percent bypass equals percent chlorine as Cl in the raw materials, raw meal basis, multiplying 100. This procedure is applied to chlorine, because it is nearly impossible to control the evaporation of chlorine in the rotary kill burning zone, or control its concentration in the process by any means. Example: the raw materials contain chlorine, raw meal basis, equals 0.23%. What is the bypass percent? The required bypass percent equals 0.25 multiplying 100, equals 25%. We follow circulation phenomenon. 4. Circulation mechanism. The circulation mechanism of circulating elements, potassium, sodium, chlorine, and sulfur can be explained in the following manner. The circulating elements enter the rotary kill, with the rotary kill feed that travels through the preheater to the rotary kill inlet. Starting from lowermost cyclones, the temperature starts reaching 8008 degrees C in the rotary kill system. From this temperature, part of these elements is volatilized, dissociated, and becomes part of the rotary kill atmosphere. We notice in this table, as the temperature starts to rise more and more, the rate of volatilization increases. In the rotary kill atmosphere, the fuel will add to the rotary kill atmosphere additional sulfur after combustion. When the material reaches burning zone, all the chlorine will be evaporated, with part from sulfate, sodium, and potassium, the harder the rotary kiln feed to burn, the higher will be the evaporation rate of the volatiles, and this takes place also in case of a very strong flame in the main burner, and transported along with the rotary kiln gas back to the areas of lower temperature. Because of this cyclic mechanism, the circulating elements increase in progression. This enrichment continues until the total quantity of circulating elements brought into the rotary kiln system corresponds to the total quantity carried out of it. The dissociated components become then capable of reacting with other compounds in the rotary kiln gas, rotary kiln dust, and burning material. The main compounds made are. See this table. Chloride reacts primarily with the alkalis, forming NaCl and KCl. Any excess of chlorides will react with calcium oxide, available in the system, to form CaCl2. A part of the alkalis in excess of chloride combine with sulfur to form Na2SO4, K2SO4, and double salts as Ca2, K2SO4, 2. Alkalis not combined with chloride or sulfur are present as Na20 and K20, embedded in the clinker mineral. Sulfur in excess of alkali combines with CaO to form CaSO4. At temperatures between 800 and 1208 degrees C, these compounds condensate on the burning materials, rotary kiln dust, or on the walls of rotary kiln and preheater system, some of them in a melted phase. The circulating elements, which condensate on the walls in the preheater and rotary kiln tube and on the burning materials, and some of these on the dust, reach areas of high temperature again, together with the burning material stream, where once again some are volatilized and transported back with the rotary kiln gas. As an example of how the concentration of a certain volatile element changes through the process. If we introduced I kilograms of potassium each hour with the feed, and when the reactions achieve a state of equilibrium of volatiles in the system, then we will have the following condition. 1. 0.811 kilograms of potassium will leave with the clinker. 2. In the system, the concentration of potassium will be 2.573 kilograms. 3. In the bypass dust, the concentration of potassium will be 0.221 kilograms. 4. In the exhaust gas dust, the concentration will be 0.042 kilograms of potassium. The explanation is the following. The first, 0.189 kilograms, will remain from 1 kilograms. This will start making accumulation, and continue on for hours with addition of new supply from the fresh material. When the concentration in the rotary kiln atmosphere reaches the concentration of 2.573 kilograms per hour, then what is coming out from the bypass system dust will be 0.221 kilograms, and with electrostatic precipitator dust, 0.042 kilograms per hour. The second, the volatility of potassium permits for the remaining of 0.811 kilograms per hour in the clinker coming out from the rotary kiln, while only 0.189 kilograms remained in the system, but eventually it will return back to the system, with the rotary kiln feed enriching the system with potassium to reach higher concentration of that element, and eventually will reach saturation level, if the bypass system is not applied. The explanation is the following. The third, the bypass system permits only for controlling the volatile elements, but not eliminating them from the system, since the concentration of the potassium coming out with rotary kiln bypass dust is only 0.042 kilograms per hour, for each 1 kilograms added to the system through the fresh feed, while nearly 0.800 kilograms is going out with the clinker. That indicates the less the volatility of the element in the raw mix in the rotary kiln, the better will be the condition regarding the circulation phenomena. We follow circulation phenomenon. 5. Evaporation rates of different elements. Each of these elements will have its evaporation rate or volatility. Volatility or evaporation factor defined as E of a volatile element or compound means that part of this element evaporates in the rotary kiln burning zone instead of leaving the rotary kiln, with the clinker produced in the rotary kiln burning zone, where this element is evaporated. The evaporation factor, E equals We follow evaporation rates of different elements. Example 1. The concentration of the sulfate in the clinker in one sample is 1.05%, SO3 concentration in cyclone 4 materials, which is collected from the material pipe of cyclone 4 to the rotary kiln inlet is 2%, and the loss on ignition of this same sample is 3.5%. What is the evaporation factor of sulfate, SO3, in this system? Solution. Percent SO3, at the kiln inlet loss on ignition-free basis, equals evaporation factor, E equals This calculation can be applied to any of the other volatile elements as potassium, sodium, or chlorine. We follow evaporation rates of different elements. Example 2. The loss on ignition of the sample for chlorine is 3.8%. Its concentration in the clinker is 0.03% and its concentration in the hot meal, kiln feed, from cyclone 4 to the kiln inlet is 0.65%. What is the evaporation factor of chlorine in this system? Solution. Percent chlorine at the kiln inlet loss on ignition free equals evaporation factor, E equals We follow evaporation rates of different elements. Example 3. The loss on ignition of the sample for potassium in rotary kiln feed is 3.5%, and the concentration of potassium in the clinker, 0.29%, and its concentration in the hot raw meal from cyclone 4 to the rotary kiln inlet 0.39%. What is the evaporation factor of potassium in this system? Solution. The percent of potassium at the rotary kiln inlet loss on ignition free equals evaporation factor, E equals But we have to indicate what is the meaning of the value obtained from the previous. We follow evaporation rates of different elements. When E equals 1, indicate that all volatile elements evaporate, and none leave with the clinker. This is clearly indicated in the case of example 2 of chlorine, where the solution proved in an unmistakable way this fact. E in the example is nearly 1. When E equals 0, indicate that none of the volatile elements evaporate, and all leave with the clinker. This is clearly indicated in the case of example 3 of potassium, where the solution proved in a very unmistakable way this fact. E in the example is very small. We follow evaporation rates of different elements. Average evaporation factors. Average values for the evaporation factor of various volatiles element compounds are: evaporation factor E. We follow evaporation rates of different elements. The volatile matters escape through the preheater dust, preheater valve. We follow evaporation rates of different elements. The volatile matters escape through the preheater chimney, preheater filter valve. We follow evaporation rates of different elements. Chloride compounds KCl, CaCl2, and NaCl are seen to have an evaporation factor of 0.990 to 0.996 in the rotary kiln at 8008 degrees C. These compounds melt and boil at 1400 degrees C. But sulfate compounds with alkali as K2SO4, potassium sulfate, and Na2SO4, sodium sulfate, will be more stable than CaSO4, calcium sulfate. The last component is formed when there is excess sulfur that cannot react with the alkali in the system. Alkali sulfates have evaporation factors from 0.2 to 0.90, but they are mostly in the lower part of the range, while excess sulfur that cannot find alkali to react with has an evaporation factor of 0.75, therefore it is best that all sulfur react with alkalis to the highest extent. Thank you for watching, and I hope these courses are helpful to everyone. Subscribing to this channel Cement Industry Courses would be appreciated. Thank you.